Continue on with chapter 1 in the book. And this is our first code that we're going to look at. And it's called binary coded decimal. Or most people just refer to it as BCD. This is not a numbering system, it is a code. It is not weighted, it's not a numbering system, it's a code. It's not a numbering system, it's a code. Does everybody understand that? Huh? It holds a coded, we'll look at it. Let's look at it first and you'll understand that. But when we use a code, we use something to represent something else, right? You understand that? But normally we don't have a chart for BCD, even though I've got one over there. So if you look at your chart, you see under binary over there, over BCD, I got yes over on the, and then I start saying, well, no. Those are not legal. Those codes are not legal in the BCD numbering system. So what we do, and this is what's going to happen, I guarantee you somebody in this class is going to try to go from decimal to binary, and what they're going to be doing is going from decimal to BCD. BCD is not a numbering system, it is a code. You cannot go from decimal to binary without subtraction. Everybody understand that? So what we do on BCD, it's not a numbering system, it's a code. If we come over here and we take a decimal number, like 965, this is decimal. If I was going to go to binary, I'd have to write down a powers of 2 chart, and I would have to subtract powers of 2's. The decimal equivalent of powers of 2's. On BCD, you cannot drop leading zeros. They are part of the code. BCD, we purposely split the codes between with spaces. So this would be BCD. 9, 6, 8, 5, 5. BCD. That is not a binary number. That is a code. If it was a binary number, I'd go 1, 2, 4, 8, 16, 32, 64. And I guarantee you, when you add your powers of 2's, you're not going to come back to 9,685. BCD is a code. We sacrifice, so there's no such thing. If I come over here and did this, you miss it. If I was to come over here and take that out right there and put a 1, that cannot be a BCD number. Because BCD numbers, the codes go from 0 to 9. There is no such thing as a single 4-bit pattern representing a 10 in BCD. BCD is not a numbering system, it is a code. But it's pretty easy to go through because what we're using 4-bit patterns that can only go from 0 to 9. They can't go from 0 to 15. They only go to 0 to 9.
We see a number like 9685. With base 10 at the bottom, we already know that. We should know that BCD code.
You should know the pattern. But
I'm saying the base 10 will give that, will let you know that that's code.
No, this lets you know that's a code. That's base 10. But base 10, I can say, okay, let's convert that to binary. Base 10, okay, let's convert that to hexadecimal. And you'd have to go through subtraction, right? You understand? You'd write your binary pattern up there, 1, 2, 4. So just because you see 9685, that is decimal. You don't know that's not BCD, that's decimal. BCD is a code that represents that decimal number. Understand what I'm saying? So 9685 is a decimal number. That's not BCD. That's a decimal number.
10, base 10. What does that mean?
Okay, so I'll explain this again. This would be legal. This number right here would be legal in two number systems. This would be legal in decimal, and it would be legal in hexadecimal. The problem is I need to let you know what base I'm writing up here. So what I'm doing is I'm putting these little subscripts out there. So if I come over here and wrote, if I came over and wrote this number right here, what base is that? Well, it could be this. Just because you see a group of ones and zeros, it don't. If that means that would be no such thing as that decimal number right there. If I saw ones and zeros, that would be so in decimal that would be equal to 1,000, right? You understand? In binary, it'd be equal to 8. So what I have to do, guys, is I have to let you know to make sure you understand what base I'm writing these numbers at. So 9685 could be a legal number in decimal, or it could be a legal number in hexadecimal. But the weight of the number would be a lot more if that was a hex number, because I have 16 combinations, than if I do it in decimal. So that makes sense. So yeah, I could come over here and I can do that.
Could you write down the binary for 9685?
What's that?
Could you write down the binary for? I mean, not the binary. Yeah, the BCD. The BCD.
Not the BCD. If I want to do the binary, what would I have to do?
No. I need the BCD for 9685.
Okay, but what would I have to do for binary? 1, 2, 4, 8, 16, 32, 64, right? 128, 256, 512, 1024, 2048, 4096, right? 8192. And then I would subtract the ones. Okay. That is the way I would go from this decimal number to binary. BCD, we just write down 4-bit patterns, kind of like hex. But hex, we can go, hex, we got these many digits. So hex, I got all these combinations right here. So my hex, when I use 4-bit patterns, using hexadecimal, hexadecimal is not a code. Hexadecimal is a numbering system. So if I was to come up here and write down my codes for hexadecimal, or my representation for hexadecimal, then I would use 4-bit patterns, right? You understand? 2, 3, 4, 5, that's a 0, guys. 6, 7, 8, 9, A, B, C, D, E, and F. Well, what we do in BCD, it is not a number system, it is a code, is we throw away all those combinations right there. We get rid of them. If I throw those away using 4 bits, if I throw those away, I've thrown away my weighted number system, right? You understand? Then what I do is I can use these codes up here to directly represent a decimal number. So what I would do, here's a 9, there's a pattern for a 9. So I'd write down that code right there. This is not a number system, this is a code. Then I would say 6. Here's the pattern for a 6. Here's the pattern for an 8. Here's a pattern for a 5. And then I'm going to put BCD down there because that is not a number system, this is a code. So if I was going to say, if this was a weighted number, then I would say 1, 2, 4, 8, and I would say 16. But that's not the way it works. So basically the way it works a lot like hexadecimal. Some people call this the 1248 code, by the way. It works a lot like hexadecimal, but I go 1, 2, 4, 8, and then I'd go what? 1, 2, 4, 8, and then I'd go 1, 2, 4, 8, and then I'd go 1, 2, 4, 8. No matter, and that's not hex. This is the way we would weight those, right? You understand? So then I would say, okay, this is the BCD for a 9. This is BCD for a 6. This is BCD for an 8. This is BCD for a 5. So it's kind of like hex, but I sacrifice A, B, C, D, E, and F. And that's a lot of weight, especially when you get up to this digit right here, guys. Because that's 65,000. That's this in hex. That would be times 32,000. So we just can't. But what's going to happen in this class is I'm going to say take this decimal number to binary, and somebody's going to write down BCD, guaranteed. Or they're going to take their BCD number and split it in groups of 4s, and they're going to say that my hex weight is 9658 and my decimal weight is 9658. That's never going to be true, right? You understand that? So what we've done to do BCD is we've thrown away 6 combinations that's available to us. This is not a number system, it's a code. But what it is, it allows us to directly represent decimal numbers. So we've got displays, 7-segment displays that displays numbers from 0 to 9. We communicate with those with BCD. We send them a BCD code. If we send them a 13, they do weird stuff. We have counters that count in BCD. We show you how they work. We have BCD counters that has the ability to count in BCD. We got binary counters and we got BCD counters. So we got decoders that converts a BCD code over to a code that would run a 7-segment display. 7-segment displays, by the way, and you see these all the time. You just don't know what they're called. These are displays that are basically just made up of segments like this. And a lot of devices still use these. Phones don't use them anymore. And then I can come up here and turn on that light and turn on that one and turn on that one and turn on that one and turn on that one, right? And it would display a what? A 9. Well, it would be nice if I could go directly from a code over to a device that would turn on those right segments for them. We call those decoders. So we have what we call BCD, the 7-segment decoder. That would actually take a BCD code and convert it over to the segments. So we have counters that count in BCD. We have displays that works with BCD. But the problem is it's not a weighted number. We can't do math with BCD. Can't do binary math with BCD because it's not a number system, it's a what? Code. But I guarantee you somebody in this class is going to do that. I'm going to say convert this decimal number to binary. And what's somebody going to do? They're going to convert to BCD. Then they're going to convert it to hex, and your decimal number is going to be 9685, and your hex number is going to be 9685, and that's impossible, right? Y'all understand that? BCD is not a number system, it's a code. But it's real easy. It's really, and I say it over and over, but somebody, if we'll celebrate if everybody in the class gets that right. But no, I've never taught a class of digital where somebody didn't do that. And we'd have done it on the numbering system. Somebody would have done it on this worksheet if we'd have got that one. So BCD is a method where we can directly represent decimal numbers without subtraction, but it's not a number system, it's a code.
That's the part you go right there.
Huh?
And the 9685, drop down and get the code.
That's it. That we don't subtract. And that's what we're trying to do with a code. We're trying to make things really easy, right? Now, of course, it gets complicated when we get into our more complex codes. When I represent letters of the alphabet. So this computer's got to deal with things besides binary. And when I come over here and look at my keyboard, I see it's got more than 1s and 0s on it. And it's got more than 0 and 9. So I could have a code up here, right, to represent my numbers, decimal numbers directly, BCD, but I got to be able to represent that A key. I got to be able to represent the B key, right, the C, the D, the E, the F. I've got to send pictures over the internet. I've got to be able to send different languages. I've got to be able to do that on the internet. We got to have what? codes. So the first code, we were fundamental. You know, we set up. Of course, the first code we had was Morse code, right? And that was a sequence of dot and dashes. But we don't use Morse code in computers because it would be hard to do a dash, right? Understand? We can do dots, but we couldn't do dash. So what they decided to do was to come up with another code, where especially when we send groups of information or when we send them. So we got two ways that we can send data. We can send it in what we call parallel, which means every bit that I send would have its own conductor. Or we can send it in what we call series. Series means we send everything, but we send it over one conductor, right? Plus a comma. Through the media. So like your cell phone information, is it parallel or is it serial? Well, parallel means we would have to have, if we was doing 16 bits, we'd have to have 16 have 16 airs in here. So the media we're sending our data through has one media, it's air. So everything we receive through the air is serial. They send it one bit after the other on a carrier. So it's serial. Inside this computer though, what do you think it probably is? It's probably parallel. But what we're doing, the code itself, whether we send it serial or data, and I don't know if we'll have time to get in some of the communication techniques. The first numerical code we're going to look at is, here's a numbering system. I don't know what chart this is. I don't know if y'all still got the same version. It should be in the book, chapter 1. And what we're doing is we're looking at numbers in 4 different number systems. This is not a number system, it's a lot. So you see there's quite a bit of difference between the binary and the code. So over here, 15 would be equal, or 14 would be equal to 1110. But on the code, it's going to be 00010101. Over here, they include the 3 zeros because it's part of the code. So on a BCD, you don't drop leading zeros because they're part of the what? Part of the code. But over here on the binary, we drop leading zeros. They should have done it here because I can drop these and that's not part of the code, right? Or not part of the numbers. So the next thing we're going to look, a code, a system of words, letters, figures, or other symbols substituted for other words, letters, acronyms. Acronyms is when you use the first letter of each pertinent word in a phrase that pronounces as a word or substitute letters. Now, technically, if you look up an acronym in the dictionary, it's going to say we take a phrase, right? You understand. And then we take the first letter off of each word, and that's supposed to form another word. So this code right here, ASCII. So that's a true acronym. Because what I did is I took American Standard Code for Information Interchange. So that's what ASCII stands for. And they drop the 4 because it's not a pertinent word and it messes us up, right? For information interchange. Then they came over here and they took that letter, they took that letter, they took that letter, they skipped over 4 because it wouldn't make another word and it was not a pertinent word. And then they came up with the acronym for ASCII. Now that's a true acronym. But what has happened in computers and what has happened in life is basically what we do now is we call them acronyms, but we'll take anything like SEC, right? We call that an acronym, even though technically you very seldom hear people call it SICK, right? So serial ATA, all types of different types of things that we use in computers, where they'll just call out the letters of the pertinent words and it don't form another word. So acronym is truly, you need to form another word. But like I said, a lot of times in computers and also technology will just come up with a phrase and we'll just pick off the first letters and then we'll just repeat the first letters off the first. ASCII, American Standard for Code Information, the most common code used for text files in computers and on the internet. So originally ASCII was the code on the internet. That was it. Everything. We learned how to, y'all ever heard of HTML? So there's an acronym. But we just called it as a hypertext markup language. Originally that's the way we send everything over the internet. And that's still the way we format. And it's not a programming language, it's a formatting language. It doesn't have the ability to do math, it don't have the ability to do anything. It's just that you can send letters, you can do punctuation with it. Of course, we lost ASCII is still around there, and it's also part of the newest code that we call Unicode. But what we have to do, unless you play around with this a lot, we have to look this thing up on a chart. So this is the ASCII code chart that's in the text. And it's a 7-bit code. I'm sorry. Yeah, it's a 7-bit code, which means I have 2 to the 7th combination, which gives me 127 characters. Oh, I'm sorry, 128. So the way this is set up, notice the top of the chart is laid off. It's called MSB, which is the most significant bits, and then the rows are called the least significant bits, right? Everybody understand that? So the first 2 columns are what we call control codes. Like when I'm sending information to a computer, I've got to tell it when to do a line feed, right? I got to tell it to go to the next page. I got to do all that kind of stuff. So you should see a carriage return up here, which would tell it to do what? Go down to the next line. We could tell it to do a form feed, which means we'd go to another page, right? You understand? Y'all see those codes? So carriage return is this guy right here. Form feed, null, start of header, start of text, end of transmission, inquiry, acknowledge, fail, backspace, horizontal tab, vertical tab. So all these is taking my computer and telling my computer to do something, right? So nothing is displayed on the screen. So the first 2 columns of the ASCII code are what we call control codes. Now for me to come up with a code, what I would do, let's say I want to do the code for a carriage return. There it is. What I would do, first of all, is I would write down the pattern off the columns, and then I'd come over here and I'd write down the pattern for the rows. And this is a code, so normally we would put ASCII out there. That's not a number system, it's a code. So I send this code over to my computer, and my computer, I'm out here typing, I hit my carriage return, it sends the code in there to my computer that says carriage return. My line would drop down and go back to the left, right? I'm sorry, carriage return would bring it back here. You have to do 2 codes. You have to do a carriage return, and then you have to do a line feed. So when you hit that enter key, basically it would probably be 2 different codes. Are we okay so far? First 2 codes are what we call control codes. So when this information comes into, and of course, IBM don't use ASCII, by the way. They use what they call a key scan code. I'll show you what these computers use. But it's basically the same. It's just a code. So what would happen if my computer received one of these codes anywhere from what? Anything from 000 to 001FF, it would tell it it's doing something, to do something. I'm fixing to send you some text. So start a text, end of text, start of transmission, end of transmission, right? You understand that? So those are what we call control codes.
So, okay. will we use column first?
Well, look, MSB, what does that mean?
Most significant.
Most significant bits. And then we have least significant. So you're right. You'd write the code for the column first, and then you would write, then the first 3 bits would be the column number, and the second 4 bits would be the row number. So my name. So I'd start off Rich. So I'd come over here and I'd find an R. And I'd write down the column, 0, 1, 0. And then I'd write down the row, 0, 0, 1, 0. Make sense? Instead of writing ASCII, guys, I'm just going to put A out there, though, okay? So that means
So that's Rich or that is R?
I'm not, that's just R.
That's just R.
I ain't finished yet.
Same thing.
I mean, how can I send you? I've got to represent a code for every letter, right? You understand? So I can't have a code that says Rich and then have another code that stands. Think about the number of names we have in the United States. And then the length of the names. You know, some of you football players, they have to actually fold their name. And I would have a code for every name in the United States. No, but we can have a code for every letter. If I've got a code for every letter, then so that's R. Go ahead. No, this is binary. It's just that originally what they were trying to do is they were trying to send out data. And anytime we send data, we have a problem with ones and zeros, because there's so many different things that can affect the ones and zeros. So I'm trying to send this through a wire that's 15 feet long, and somebody turns on a big old motor over here, and all of a sudden something that was a 1 became a 0, or something that was a 0 that became a 1. And I could be telling my lathe to do something, and all of a sudden that sucker takes off. So what they did, now we still do this. What they did is they say, well, what can I do to have a pretty good chance that I know that the data received was the data that transmitted? The first method they came up with was something called parity. Now what they do with parity, and it's a really simple circuit that does this, is we have 2 parities that we can, and that was the 8th bit. So we were dealing with 8-bit processors, but what they did is they sacrificed that most significant bit for error checking. It couldn't correct it, but it could check it. Okay. So now we have what we call ECC, which is error checking and correction, but that's a math thing. So our hard drives and our mass storage device uses something called ECC, but it's a code that they know what was read is what was sent, right? You understand? So parity was a very simple circuit. So what we would do is we'd send the data, and then we would add a second bit that was parity. So it's an 8-bit code, but 1 bit was sacrificed for parity, right? You understand? And what the circuit would do is it would come up here and count the number. So let's say I'm running even parity. Even parity means when the receiver always wants to receive not an even number of bits. So if I'm running even parity, I'd come up here and my circuit would count the number of ones. 1, 2, 3. Is 3 even or is 3 odd? So what it would do is it would set that bit. That's not part of the ASCII code. That's for error checking. What the receiver would do, so your transmitter would be set up to send even parity. Your receiver would receive odd even parity, and when it received it, it would count the number of ones. 1, 2, 3, including the parity bit. So it would count 1, 2, 3, 4. Is that right? Yeah. 1, 2, 3, 4. And it says, well, it's even. Then the data must have been right. If it was set up to receive even parity and it received an odd number of parity, it would say error. And what it would do is it would send it, and when it received it, it would use these guys right here. Acknowledge, call it, or a NAC. So what would happen is the receiver, every byte it would send, if it came in even, it would send an acknowledge, and then the transmitter would transmit another byte. if the receiver was set up to get even parity and the number came in and had an odd number of one, it would send a NAC back to the transmitter, and the transmitter would retransmit the last data that it was seen. So it's not octal. Understand, if it was octal, then this chart over here would be what? Would be 3 bits. So what they did is it was originally a 7-bit code, but they reserved that 8-bit for parity. So let me finish my name. R-I, so what would I do now? Lowercase, yeah, we'd probably go to lowercase now, right?
With that, so, okay, look. So when you tell us to write our name, will we be penalized for making all uppercase or making all lowercase, or?
It's up to you. If I don't specify uppercase or lowercase, but usually when I write, it's usually what you do is you write your name. So when I write my name, that's the way I always write it, right? But y'all see how this would go? So this would go, I'm going to drop the parity. So that would be 110. Then I'd follow this over and I would put, well, it's technically 1001.
Okay, so on our sheet, you don't have those parity.
The what?
On our sheet, you don't have those.
Yeah, and understand what gets cumbersome with this chart that's in the book is that this is binary. So what you're going to find out is most of your decimal charts are laid out in decimal, which wouldn't let me know the binary code, or it's laid out in hex. So it would be better, it would be a lot faster if I came up here, instead of using binary. The ASCII code is a binary code, but I can go between hex and binary without hardly even thinking about it, right? You understand? So what I want you to do is we'll use hex. But ASCII is a binary code, but I can use hexadecimal to represent binary. So what I'm going to do is I'm going to come across the top and put hex up here. So this would be 0, 1, 2, 3, 4, 5, 6, 7. We don't have to go any further. And over here I'll put what? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and L. It's kind of hard on this chart. So for Rich, I would say, what? 52. And that's base 16 though. It's a code, right? You understand that? And for I, I'd come down here and I'd say 69. See how much faster that is? Now, if I needed the binary code, I mean, I could come up here in no time and write down the actual true binary code. But it's easier for us to deal with the chart if the chart is in hexadecimal. Then I do I, then I would do C, which would be 63. This chart here is kind of slow over here. And then I C, that was C, or H. So lowercase h would be column 6, 8.
So if we wrote it in hex, you will take that as well?
Yes.
Okay.
Yeah, I mean, good gracious. I would even get confused if you tried to do it in everything in binary.
Yeah,
But you got to understand, the ASCII code is a binary code. It's just that we can represent for us, right? So we use hexadecimal. This computer right here has no idea what hexadecimal is. All it knows is binary. But it has the ability to make things appear like it not is. Like this right here. It has no idea what null is because all it's doing is turning on a pattern of ones and zeros. And this is actually a picture.
So ASCII code is basically not a complex thing.
Well, it's only 8 bits, unless we go to what we call. So this is the same chart, but it's laid out in what? Hexadecimal. Don't that make it easier?
Yeah.
But you got to understand binary. And if I was going to give you a hex, if I was going to give you an ASCII code, then I would give it to you in hex because it's just so much easier to use this chart. You couldn't do it in octal because we got 16 rows, right? We can't 16 rows over there, so we couldn't do it in octal. So we have to do it in hex because of the number of rows. Are we okay? Any questions? Guys, this is still now, so let's look. We don't, uh, 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 let me go ahead and we're not using ASCII. Now we use a code called Unicode. The problem with ASCII is English. It's the Latin alphabet. And how many languages do we have in the world? A lot. More than even Unicode supports. But Unicode supports all these different languages. And so now if I could write a web page and display it in Manganese if I wanted to, right? I said that right. That's good. So, but what we're going to find out is the lower 127 codes are still the ASCII code, even in Unicode. So this is my name, and this is true. So when I come up here and type anything on this screen, it's got to be represented with a code.
So you put the space up there too.
Yeah, I'd have to have that. So we have a code for a what? Space. Because if I don't put the space between my first name and my last name, it would assume it was all one name, right? You understand?
So do you have to do it individually, or is it what is
You're like, what did you? Oh, so okay.
Space 20 base 16 is. And a lot of times you can look. So when I did HTML, if I did HTML, I would literally, I think you put a % sign in front of an ASCII code. So if I was to do that in a HTML and I wanted to display a space, then in my HTML language I would have to put the ASCII code for a what? For a space. If I wanted my web page to do a carriage return line feed, I would have to send it to, in my HTML document, I'd have to put the code for what? A carriage return line feed. You know. You can't see HTML much anymore on your new web browsers. We can see it in Blackboard though. So we'll go in there. So I do that all the time when I can't get it to format right. I'll look at the HTML up there and I can take out stuff in it and add stuff. So it's but you got to know a lot. Like the first way we wrote web pages was in HTML language. Now almost nobody does that. They'll give like Microsoft Publisher, and they'll put stuff up there and type stuff, and then it'll compile it over to HTML for you. So just about everybody now, when they create web pages, they don't use HTML. They use a translator. But originally, we did it all HTML. So I originally wrote the first web page for the college. We didn't even host it. We didn't even have internet. But there was a company in Birmingham called, it was called American Online when they first came out. And somebody else wanted to use that. Y'all heard American Online? So they paid Rocky Rollins a ton of money. So they could use his registered trademark, and he changed it to called the Metrics. And he had internet access, and he would host web pages for companies and for schools. Huh? Yeah, it was. Rocky Rollins had that name, and he made a ton of it. Rocky Rollins, he's probably passed away now. But he was a cool guy. So he hosted our webpage for Bessemer State Technical College. And we had to upload it and download it through modems, through dial-up modems. 9,600 bits per second. And the college didn't even have internet. We didn't have internet. So let's see if y'all can do that. Now is the time. Currently available. So even emojis down here somewhere. So I have to have a code for emojis, right? You understand that? Emojicons. Now these are the ones that's supported by Unicode, but there's something over here where it says private area use. So they've got where different companies can come up with their own codes for, especially for emojis, because we've got all types of different phones out there that has those available. But these are the only emojis that this Unicode supports. At this version, I don't know how it pops up. It should. Oh, so these are, and of course they've got theirs in decimal. So what you'd have to do here is you would have to take this decimal number, which is, I think it's decimal. Let's look. No, it's X. See, it goes through F. We deal with, of course, the Latin alphabet. But just about every scripted language that's available out there has a what? So here's European script, here's African scripts, South Asian scripts, Indonesia, East Asian scripts, Middle Eastern scripts, Southeastern Asian scripts. We're down here in Latin. Mathematical, so all your math operations has to have a what? Has to have a code, right? You understand that? And this is Unicode. So ASCII, the problem with ASCII is that we have very few symbols available to us because it's only a 7-bit code. Unicode is big. I'm looking for the Latin alphabet. Symbols, Asian. So you get the Latin, I think. We get the Latin, I think. I'm not sure if we get this one or not. I know we get math. We get a lot of math symbols when we install it over here. And so here's all the Unicodes that's supported by Microsoft Windows. I mean by Word. This tells you where the scripts come from right here. The ones you use most often, it'll put it in this recently used. You can do them with a key, if I can remember how to do this. So that's that guy right there. So according to that, we can say my Alt key. We do 1 F 4 8, and then we get Alt plus Alt X. Yeah. Let's see where it's telling you how to do that. Right here. So here's the short key. You can look it up in the chart, but if you use these codes all the time, you would eventually learn that what? That 1 F4A, right? You understand? Then what you do, you hit Alt. Once you enter the code, you hit Alt. Hold it down when it says plus, and you hold it down. Then you hit the X key, and then it will convert it over to that character. So that's the shortcut. So like if I wanted, like 5/8. So 5/8 is what? 215D. I would come over and type in 215D, and then I would do what? No, I'm sorry. I was still in my code chart. 5/8. So I'd come over here, right? And type in what? 215D, right? Then I hit what? Alt X, and then you did 5/8. So that's the shortcut for going between Unicode. With that, you can see why that would be beneficial if you use the same codes all the time. First of all, you look for it here. You've only got so many recently used. So once you fill this up, So that's Unicode. which is basically a subset. So, but ASCII's still in here because there's a lot of websites still written over here and nothing but what? ASCII. So you look the first codes. So if you look on your chart and you look at the code for an uppercase A, what's the hex for an uppercase A? 41. Well, see, there's the Unicode for uppercase A. It's what? 41. Except it's 4 characters. But then my lowercase I is 69. So ASCII is still a subset of Unicode because there's a lot of websites out there that's written in ASCII that's been out there for years. This is the Keyscan code. This is what these computers use. So when I type a key on my keyboard, it sends a code. This is in hexadecimal. So when I hit the A key, it's going to send 16 with its uppercase lowercase. The way it works is if you hit this key, it gets the code 12. Then it sees a 1 it's going to give you an uppercase A. If you don't have a shift key pressed, it's going to give you a lowercase A. So this is the same code it gets for an A with its uppercase lowercase. And that would be on the top. So this is the Keyscan code. This is used by this computer right here. And then we've got other codes. We got a counting code called Gray code. And we might talk a little bit about that. We'll definitely talk about that if you take PLCs. It's a counting code, but it's a high-speed counting code. And it's a code, but it's ones and zeros. So y'all got any questions on that? So that's that chapter. Okay, y'all take a 10-minute break and start in the next chapter. I think I told y'all this book is available online, right?
How much is it?
I think it's $54, I think, online. I know y'all can go to the bookstore and look up the course number and give you the price.
So it's only $54 online, and that's the buy it?
No, that's the rent.
Yeah, okay. Yeah.
So I think it's good for 180 days. And then after that, you'll lose access to it.
That won't be bad.
Yeah. You hopefully got a computer at home. It'd be hard to read this book on a smartphone, right? Unless you got a pair of Gilbert's glasses. We got some of those over there. But if you, I've got every technical book I had in college. I got all my math books too. I still have to use them every once in a while because my grandkids will come in and won't help with their math, and I can't remember how to do it.